Thank you. I'm going to present about IMES. It's called Indoor Messaging System. And this is a technology developed for indoor positioning. As you have already heard from some presenters before that, there are different like Wi-Fi and other different technologies, but we still have problems to do good indoor navigation or indoor locations. And if we look at the situation till now, or a few years back, we would like to have the indoor navigation solution, some system, but there are no such existing things. So we use whatever was available, for example, Wi-Fi signal or Bluetooth or RFID or tags and also the AGPS systems. But they have their own limitations and they have their own problems. Of course, they have some other merits. And due to those limitations and some problems, so we work on the navigation solutions, what we can do on that. So based on those problems we analyze, then we have developed this IMES technology. And now I'd like to show you some of the characteristics of the IMES. First, we'd like to have a technology that is compatible with the mobile phones, because we use a mobile phone for many of our location-based applications, and they will be used for other uses as well. And they already have a GPS built in. So we'd like to have a system that is compatible with the existing GPS receiver. Then we thought, okay, then we have to base the technology based on the GPS or the GNSS signal structure. So what we did is the simple idea is, okay, let's replace the navigation data of the GPS signal by the position itself of the transmitter. So we transmit the position from the transmitter itself, remaining all the signal structure as the same as the GPS signal. Then another requirement will be seamless navigation. The device should be able to do the seamless navigation whether you are outside and inside. When you are outside, you can use your GPS receiver or GNSS receiver. And when you go inside, then it should be able to give you the same level of accuracy or positioning solution. And that is what IMES can provide you. And we don't want to make the position computation complex, because you have always the problem of the power consumption in the mobile phones. So the biggest issue is how much power it requires. So we want to reduce the power, or we don't want to add any extra power consumption on that. That means we don't want to do any pseudo-ranging calculations at all. And also we don't want to do any change in the hardware, because the manufacturers, they will not be happy if they have to modify the existing hardware on the receiver. So, and just we put one transmitter unit, so you get a 3D position, because we transmit the position itself, and that includes latitude, longitude, height, and also the floor information, and that is different from other solutions where you don't get the floor information. And another thing is it can provide you a very stable accuracy wherever you are, or whenever you measure it. So you always get the same level of accuracy. If one device covers an area of 10 meters, you always get the accuracy within that level. For example, if we have a transmitter in this room, one transmitter, so whether you are in this corner or that corner, you always get the same position. The position will not vary based upon your location or time. And since we use only one transmitter, so we don't need to do any clock synchronization. We don't do pseudo range, so we don't need any clock information. So you just decode the navigation message and you use the position, whatever you get from that. That's the characteristics of the IMES. And this is a simple slide to show you the seamless 3D navigation. So when we are outside, so we have a GPS and QGSS satellite, so we can do a normal positioning. And when we go indoor, then we use the IMES signal. And also when we go deep indoor, or like the underground garage or parking areas, we still use the IMES. So when you move from outside to inside or from inside to outside, if we have IMES, so we can have a sort of a seamless navigation solution. And this is a basic difference between GPS and IMES signal structure. As I mentioned before, that the center frequency GPS and IMES is the same, but we have shifted by 8.2 kilohertz for IMES to minimize the interference to weak GPS signals. And there are 10 PIN codes allocated for IMES from 173 to 182. This is for L1CS signal. And these PIN codes are already documented in the document published by the US government in the ICD, GPS ICD document. And other things are same. But in the navigation message, we can make it variable if you would like to have it. So currently we use a 50 BPS, but we can also have a choice of 250 or 500 BPS of navigation message rate. So this is the basic difference between GPS and IMES in terms of the signal structure. And we have already developed the IMES chip. And one which is shown here, we have IMES core module and IMES transmitter. Then on the bottom we have IMES transmitter chip, and also we have this IMES GPS receiver. So the spec on the left side, you can see the specification of the IMES chip. It has the frequency is same, and this chip can have 2 channels. It can output 2 RF signals, 2 PIN code signals, and also the bit rates, navigation bit rates are variable. But in order to use IMES, we have to deploy the transmitter device. Like in this room, we have to deploy maybe 1 or 2 units. And when we need to deploy the transmitter devices, we need to have some sort of a management system. We just can't fix the IMES transmitter and use it. It has to be managed, it has to be controlled. So in order to do that, we have developed all the necessary tools. For example, on the left side top, we have IMES transmitter management tool. We can use this tool we use to set up the PIN code, power level, frequency, offset, and other navigation messages that you want to broadcast. So we can use this. And on the right side top, we have a coordinate generator tool. So just before, in the previous presentation, we heard about the requirements of the maps, raster maps or vector maps, and different sorts of data. So you need a floor map, you need a building map of the area where you want to do the navigation. So in order to do that, we have made a tool to generate maps. It can be, your input can be either vector data or raster data or even the paper drawings. Then we can scan it, rasterize it, and convert to vector data and make IMES necessary data for the IMES system. And on the bottom right, we can see some propagation simulation tool in order to set up how many transmitter devices to cover the whole area. We have to do a sort of simulations to find out the optimum location or optimum power level so that we can have a best solution, best deployment possible. On the bottom left, we have the whole database management system. So this will manage the complete database system of the transmitter, of the mapping data and the power levels, all the history data, who has installed, when it was installed, when it is removed, when it is changed. So all these data have to be managed. So we create such database systems. And this is just one experiment output, experiment data showing that how much signal power you transmit and how much we can cover by one transmitted device. So the maximum power allowed to transmit in Japan by the regulation is minus 64 dBm. EIRP power is minus 64 dBm. But we normally, to cover about 10 meters, we transmit about minus 76 dBm at the antenna, EIRP power, and it will cover about 10 meters radius. That is shown by this yellow, these semicircles on the upper right. And on the bottom, we have shown some graphs that we actually transmitted the signal and measure the signal. the CN0 in different locations for different power levels. So you can see at very low power, minus 79 on the left bottom, so it covers about 3 or 4 meters. And if you have about minus 73 dBm, it's about 10 meters or 12 meters radius coverage. We can see from the graphs. These are the actual measurement data. And I mentioned that the IMES signal, the center frequencies are offset by 8.2 kilohertz. This is to minimize any possible interference to GPS signals, especially considering the weak GPS signal, because the AGPS, some weak signal receivers, they go down to maybe minus 145 or minus 155 dBm signal processing, but they need to do integration. So the longer the integration, the better. You can see the graph below. So we can avoid the interference, possible interference to GPS by shifting the center frequency a bit. And this is a comparison what we did with using the IMES device in the indoor area and with the different mobile phones available in Japan, from different makers. And we put side by side all the mobile phones and IMES receiver and transmit the IMES signal, and also do the positioning using the hybrid solution, Wi-Fi and probably Wi-Fi and the cell data. And on the bottom, it's only by GPS. So if we look at the IMES data, so because we transmit the position itself, so you always get the same position in that area. So it doesn't change with respect to time. So this is what we get from IMES. So this is what we call the stable accuracy. So if your accuracy is within 10 meters, so you are always sure that you are within 10 meters from that area. So you don't have to worry whether you are 100 meters off or 10 meters off. So you don't have to worry in case of IMES. And it also gave you which floor you are. But in the case of other solutions, so we basically have a 2D solution, and they change with respect to time. And if you don't have a good access point database, so sometimes you have a different city zone on your device. So this is what we can see here. In the middle, we can see that the position is very near to the true position, but it's a little bit offset. And on the right side, the most right, the position what you got is almost accurate to where you are. But if you use only GPS, of course, it's indoor, so we have a lot of offset from the location where you are. So this is a sort of a comparison, and we did a lot of such experiments for some applications that I will show you later. Now we move to some of the applications that we are doing in Japan. So in Japan, as Frank earlier mentioned, that it's legalized in Japan to transmit IMES signals, and there are already many applications coming up. And this is one example in a very recently built new shopping mall in a nearby Tokyo area. It's called the Rise Shopping Mall, managed by the Tokyo Railway Corporation. And you can see the picture. There's a huge building, a very huge area on the right side. And we'll install within this year IMES in all the floors. So last year we have already installed some devices for demonstrations, for testing, for application developers to use developing their applications and testing their applications there. But in this year we'll install IMES in all the floors, and this will be a sort of a showcase for the IMES applications, not only for Japan but for also the other users or other developers and manufacturers all over the world. So they can come here and see how IMES is working and what they can do and what are the merits or benefits or what are the limitations like that. And this is another applications for the digital sign. This device on the right side, which is shown a picture here. So we'll have IMES transmitter installed in this box, and they are located in the railway stations, entrance, exits, ticket booths, and subways. All the indoor areas we have such maps at the moment. But at the moment it's just a paper map, and there's no such digital signals. But from now on, we'll have such IMES enable digital sign, and if you go near to the board, so you get the map in your mobile phone transmitted from that device. We have IMES installed in the device. And after that, you have different types of applications you can use. So all your location-based services applications you can use. You can do the queries. You can find out where you want to do and navigate yourself inside the buildings, underground area or parking area, wherever you are. And another application is in the medical applications for managing the medical services in the hospital. And recently, there is a public organization formed. It's called the Community Health Informatics R&D Organization. And this is chaired by the doctors from the Gifu University. And there are other, you can see on the bottom, there are 3 groups of the people. One is from the public service corporations. We can see all the medical related associations, Japan Medical Association, Dental Association, and so on. And in the middle, we have the people from the academic sectors who develop the systems or who make the regulations of the systems. And on the far left, right, we have the people from the industry. And also GNSS technologies, we are involved on that. And there are different industries. And all the carriers in Japan, Entity, Docomo, Entity, KDDI, SoftBank, and all the carriers, they are also coming here. And if you look at the current problem in Japan in the medical sector, the first thing is the people are getting, the number of people who are getting aged is increasing very rapidly. So by 2020, almost every 1 person in 3 or 4 will be an aged person. That percentage is about 30% by 2020. And the government is now planning to have a better system for the care service for the aged people. So in order to provide such services, the government would like to have a system that can manage the services to the aged people. And another part is also to manage the resources in the hospital, to provide to manage the medical staffs in the hospitals, to deploy the doctors or nurses in case of emergencies from one place to another places, and also to monitor the equipments and devices and so on. So this is one example of the home care systems using IMES and GNSS GPS. So this home care service demand, the demand at the moment is about 2.9 million people. They need a home care service at the moment. And every home we plan to transmit, we plan to install 2 transmitter devices at the entrance of the home and in the living room of the people who need a care service. And this shows the number of hospitals. That the total number of hospitals in Japan is about 8,600, and all the government has already decided to provide such systems all over Japan, and the prefectures will have decided to install the IMES system in the hospitals. So this year we will install the IMES-based system for such monitoring and services, at least in 2 prefectures in Japan. Another application of IMES will be in the pollution monitoring for asbestos. Because in Japan there are some buildings that were built in the past, and they have asbestos, and asbestos is known to cause cancer. So they would like to do the rebuild or redesign it. And in order to monitor the amount of asbestos that is coming to the air, they need to monitor it constantly, at least once a year or twice a year. And they need to know very precisely the location and the time when they monitor and what is the level of the pollution. And the Tokyo municipality has already decided to use the IMES-based system for such monitoring, and the demand will be at least 100,000. This is only for the Tokyo metropolitan area. So at least 100,000 houses we have to monitor. But if we consider the whole Japan, the volume is quite large. And finally, we have a consortium to discuss about the specifications and its applications, and also for the promotion of the IMES. And there are about 100 industry members and 160 individual members. Thank you.